Okay, welcome to the Citizens Water Advocacy Group monthly public program for February 2019. Our speaker today is Dr. Michael Crimmins. He will talk about drought in Arizona, observations, impacts, and projections. Dr. Crimmins is a climate science extension specialist and associate professor at the University of Arizona, where he provides climate science support to resource managers across Arizona. He's also a principal investigator with the Climate Assessment for the Southwest. He will discuss the unique aspects of Arizona's hydroclimate that control precipitation variability at both short and long time scales. He'll explain how increasing temperatures relate to drought conditions, and will explore climate model projections for Arizona and what they mean in terms of potential changes in temperatures and precipitation patterns in coming decades. So CWAG is a water group, and we're here now presenting a climate change program, because we now understand that climate change is going to affect safe yield, it affects the recharge for the Prescott AMA, it affects the overdraft in the Prescott AMA, and it affects the future of the Verde River. So this is a very important topic, and we're very grateful to have Dr. Michael Crimmins come and speak. Okay.
This is great. No? Sorry? Okay. Try not to swallow it here. Can you hear me? Is that working? Does that work? Okay. Great. Okay, so thanks for having me back. I think may have been 10 years? 8 or 10 years? I'm a lot grayer than I was the last time. I've seen pictures of that talk. Thanks for having me. This is really exciting. I'm excited to talk to you today. And let's just get right into it. So I think what we're going to do today is first turn on the slide. Trying to get any feedback. Go right into it. Is that working? Okay. All right. I move around a lot. So what I want to do today is I'm going to try to move slowly and deliberately through these slides. I usually try to pack 60 slides in an hour talk, and I really tried to think about what are the key points, and I may get done early, so then we could actually field questions. Because this is a big topic. When Ed approached me, I was ready, I was up for it, but then it took me a long time to think through what was the deliberate order of slides and the thing. So this is my best shot at it, and if it leaves some dangling questions, I will do my best to sort of field them afterwards. If you have any quick questions on clarifications, on definitions, let me know. But if it's any longer type question, we're going to save that for the end so we can get it on camera. Okay, so I start here. And the arc of this presentation is from a climatologist's perspective. If I start talking about stream flow and groundwater, stop listening to me, because I am out of my wheelhouse, all right? I will touch on some of those things, but I'm in the sky, I'm in the clouds. I'm thinking about inputs to the system and a little bit about the forcings on the system and taking the water out of the system. So when I give talks, I really like to try to walk through what are those pieces and parts of Arizona climate, because they're very, very interesting from the Southwest if you've heard me give a talk before. We have aspects of topoclimate. I'm from Michigan originally. We do not have topoclimate in Michigan. We don't have topography. When you have topography, you drive very interesting spatial patterns over short distances, and we know that. There are snow up on some of the peaks and very kind of lower elevation spots around the valley right now, and I came up from Tucson. We don't have snow down in the valley. So over very short distances, even in Tucson, we have lots of water at the top of the Catalinas, and we don't have it down in the lower parts of the basin. We also have seasonality. It's this idea of monsoon versus winter storms. Other parts of the country don't have that. California does not have seasonality in their precipitation in the sense that they have two different seasons that can compete or contrast or contribute to their water balances. They have a Mediterranean climate They have winter precipitation, and that's it. If they miss it in a year, they're in trouble. If they get a lot or too much in a year, they're in good shape. We're actually seeing the whipsawing back and forth over the last 5 to 7 years in California, where they're in epic drought, flood, epic drought. We have a little bit more of a nuanced pattern here, and that is a good thing for Arizona, and I think makes us a little bit more robust in the long term. But again, I think that kind of the punchline of this talk is vigilance. It's vigilance through the wet periods, and it will get wet again here. That's part of the longer term climate variability here. And that's actually softballing myself into this next bullet point, El Nino Southern Oscillation. Our longer term climate variability from a precip standpoint related to wintertime precipitation is related to La Nina and El Nino, the Southern Oscillation across the Pacific Ocean. And its seesawing will actually drive changes in the winter jet stream and can lead us into a wet winter or into a very dry winter. So last winter was a La Nina, and we will talk about that. And last winter was a very, very dry winter. And then climate change. So this kind of creeping crud, the background subtle changes, primarily in temperature right now, the creeping crud of warming temperatures driving subtle shifts in the background water balance. That's the thing we need to be paying attention to. Also, in the longer term, probably shifting some changes, maybe in El Nino. The science isn't real certain on that. A couple of papers have come out recently that suggest that El Nino is going to become more intense and will become stronger. So we may end up having whipsawing between El Nino and La Nina with intense El Nino events, which would be wet for us, and intense La Nina winters, which would be dry for us. So that could be increased hydroclimatic variability. But on that end of the spectrum, in climate science, precipitation is a real challenge for us. That's really where we have a lot of work to do. Increasing temperatures, it's fairly simple physics. Okay, so I always start with this map. I like physical climatology maps of precipitation and temperature. And this is purely to articulate that concept of topoclimate. Okay, so the idea that you can have a watershed boundary with annual average temperatures, which are very, very cool. You'd have to go up into Canada at much lower elevations to see that kind of background temperature to support that kind of ecosystem and to support that kind of water balance, and have lower elevation areas at the mouth of the Verde watershed down here, down into Phoenix, which are low desert. Okay, so the water towers in the sky are the mountains here in Arizona, right? So we have higher elevations, they're cooler, they can force more precipitation, both in the winter, through orographic lifting. We can push up air and cool it and condense it and cause precipitation. It's in a cool area, so it won't have a lot of evapotranspiration. So we can generate surplus of water, and that surplus of water works its way down, turns into base flow in streams, and actually flows down to the lower elevation areas where I'm in Tucson, and we use a lot of that water that has been accumulating in the wintertime up at higher elevations, and it works its way down in rivers. That's the water management system of the western US, is managing snowmelt that accumulates at higher elevations. Now, in this part of Arizona, we do have snow generation here, but we're at the very southern part of the sort of the Colorado Plateau and the Southern Rockies, and we're in this transition zone where our snowpack is flaky. It's not as reliable as you get up into the middle Rockies, the Central Rockies, or the Northern Rockies. It can kind of come and go, but our system is really sort of adapted to deal with that. Snow is very important for us. We've seen changes in snow, but it's not quite the same as when you get up into the higher parts of, say, the Colorado River Basin. So this is the pattern of precipitation, again, aligning itself with topography very, very closely. So this is basically a topographic map that has been rescaled with precipitation, has a couple of subtle nuances with this. If you took this map, and I gave you this map for California, you'd see all the mountain ranges nicely, the wettest areas and the lower elevation areas much drier. And then you'd also see areas like rain shadows. We have some of those features in Arizona climate, and I can kind of draw your attention to a couple of them. The Mogollon Rim, in particular, which is also part of the Verde Basin up here, is, I like to think of it as a topographic or topoclimatic squeegee. As weather systems come out of the western US are off of the Pacific Ocean and into here, and we've had numerous of those over the last couple of weeks, which have been great. That air is forced up, and that rim literally is pulling that water out of those air masses as they go along and forcing precipitation through orographic lifting. Okay, so that topographic feature is very important in generating precipitation, especially in the wintertime, and snow in the wintertime as well. Okay, so this idea of seasonality also comes into play here as well. We have a monsoon system, the North American monsoon system, with most of its activity to the south, can have moisture come up out of the Gulf of California, also from the Gulf of Mexico, and be drawn up in convection, the rising air in the summertime heat, over mountain ranges, and then forcing that precipitation there, okay? California doesn't really have that. The Northern Rockies, a little bit of that, but ours has that stark season, which we'll look at the seasonality a little bit more. But having these two different seasons and having topography become the critical determinants of producing precipitation in Arizona in 2 seasons. Okay, so I'm going to spend a couple minutes trying to describe this graph. And I apologize, it's a little hard to read, but I want you to see that there are very faint lines here. This is a very faint light blue, slightly darker blue, a much darker blue, and then it repeats off to the other side. Okay, so what is this? This is off of a tool. So all the data that I pulled today are on these very handy web tools that you can go in and actually, yes?
Would you like the lights off?
It's up to you guys if that might help a little bit.
Help? Yeah.
Yeah, maybe that would do it. Can we grab the lights real quick? Grab a drink of water here. You see a little better?
Yeah.
Is that good? Okay, good.
Yeah.
Okay, this is a plot from an online tool called the West-Wide Drought Tracker. It takes gridded climate data that's produced every month, and that data extends back to the late 1800s. Very, very handy resource and very good data. Estimates, but still, I think, very reasonable for the crazy topo climate of the western US. So there's a little handy extraction tool here, and they actually group the salts and the verde together. So I apologize, a little bit of a mixed signal here. This is actually the verde salt together. But this is the long-term average monthly precipitation, and I started this on the water year, October, and it repeats through the end of the water year, actually just goes through the water year, through the end of September. Okay, so the climatology of values going back to 1895 to present, so each of those months for this area, that whole historic record, are organized into what we call distributions. All right, and so the distribution of the October values over this 120-ish year record is for the average for this whole area here for October, the median, which is close to the average here, is just a little over an inch for October. Okay, so, but this would be if you organized all those values in, we remember like thinking in statistics, like a normal distribution. This isn't quite a normal distribution. It is organized with most of the values are in this black line, and then the rarer the values in this direction become these lighter blues. This is the 5th to 95th percentile. So if you organized all of the values from high to low, and you looked at the top 5 and the lowest 95, would be top 90, above the 95th here, below the 5th here. So these would be record wet values, and these would be record dry values. Okay, so this is our envelope, our climate envelope that these two watersheds live in historically. This is what I do for a living. So I look back at these data and try to get context. So is it unusual? I don't know. Let's go back and look at the data, right? So that's what we're doing here. So this is October, and then we go November, December, all the way through, kind of follow the black line, into the spring and into the monsoon. Okay, so what I did here was I tried to break the year down into seasons that I see that are important for us to consider in Arizona climate. Okay, and you don't have to do this everywhere, but we have a weird climate. And to understand where we've come from, where we are now, and where we might go, we have to break the year into pieces. All right, so, and we can also, this just happened to have plotted last year. So this is September of 2018, back that previous year all the way to October of 2017. Okay, so October of 2017 had almost the wettest October on record for these two watersheds. Okay, so that was probably a tropical storm. And I can't quite remember what happened there, but I do remember this last October, as you probably do, and we had another October with very wet conditions. Okay, so I've been in Arizona since 2001, so it's almost been 20 years. And I thought it didn't rain in October. I thought that was a dry month. Well, it can be. You can't see this, but there are a lot of zeros. Not a lot, but they're not unprecedented in October here. And they're also very wet values. So October ends up being this month with enormous possibility. And if we go back in the historic records, and as I've become smarter as I've lived here, sort of, going back in the record, you see October can deliver floods of record in Arizona and a lot of zeros. So it's an interesting month. What it means from a water standpoint, I'm not totally sure, but it's this weird part of Arizona climate that floods and creates drought conditions in subsequent years. We've just had a couple of years in a row where the tropical storm activity has visited Arizona a little bit more regularly than, say, in the last 10 years, previous 10 years. Okay, so tropical storms here in October. Then we move into the winter, quote, air quotes, wet season for Arizona. This is our winter season. I want you to see here, though, that the variability of winters is enormous. The background variability of Arizona winters is enormous. There's no such thing as a normal winter in Arizona. There's a lot of hitting the guardrails. There's a lot of dry winters, and there's a lot of wet winters, and there's a lot of crazy wet winters in a record. I say lot very gratuitously here. This is the actual distribution here. But this middle part of the distribution is wide, which means that regularly you're getting fairly wet values and fairly dry values over time. That is actually El Nino and La Nina operating on our climate. It also, I want you to draw your attention here too, is that this distribution ends up having enormous values up in the higher range for the winter, even bigger than the summer, and very dry conditions which aren't all that different than late spring. So we can end up having winters that do not show up, right? We actually had one last year. Winter didn't show up, okay? Is that unusual? It is in the record. It's not unprecedented. Is that climate change? Probably not at this point. Probably natural variability. Okay, so spring, I think, is a generous term for, it's beautiful up here. Tucson, it's a very generous term. Phoenix, it's probably not a normal term to use. It's also known as arid foresummer, honest to goodness, in the scientific literature, arid foresummer, as the April, May, June period. Hot and dry. And you can see here that this dip in precipitation, the break in seasonality from the winter before the summer, is very pronounced and very reliable. Right? That's the natural progression of the climate system in the western U.S. reorganizing. The winter storm track moving away from Arizona, being replaced by a high pressure system, heating up. The western U.S. heats up under an increasing sun angle, and then the monsoon system moves in and replaces underneath that high, has moisture come in. So we have a real pronounced movement from June to July as that monsoon moisture comes in. Interesting though, look at the spread of this inner part of the distribution, which is very wide in the winter, is not very wide in the summer. This is a little counterintuitive. It never rains at your house in the summer. I know that. I heard that. I hear it every summer. It has not rained at my house, right? And that's the way the monsoon works. It rains at every other person's house every other monsoon. So on average, it ends up raining everywhere all the time. And honestly, as you go look at the records, the reliability of the monsoon is quite good. It's very high. Tree ring record reconstructions also show that the monsoon never doesn't show up. It always shows up. It's never as good as we want it to be, but it always shows up. So there's a reliability in the monsoon signal. The climate projections are very all over the place on this. They're leaning towards probably more of the same, all right? But the science has really got to work hard at this, and the papers are kind of all over the place because it's such a complex system. Okay, so that is your breakdown of topoclimate and seasonality. So whether you like it or not, you live in a place that's really complicated hydroclimate-wise, and it's not going to give you any easy answers for the future. That's the real challenging part of this. Okay. Maybe that's all I get to talk about today. No, I guess so. Okay. All right, so let's make a little finer point on the winter side of this variability. You've all heard of El Nino. You've all heard of La Nina, I'm sure. It's in the newspaper. It's in the reporting. So what the heck is it? Okay, so real briefly, without a lot of graphics, I'm just going to kind of go to storm tracks here. Across the Pacific Ocean, there are little blobs of warm water and cool water, okay? And under normal conditions, there's cool water in the eastern Pacific and warm water in the western Pacific. And that has to do with the easterly winds pushing the water away from the South American coast, causing upwelling, piling up the warm water in the West Pacific. And that causes thunderstorms to occur in the West Pacific. Those thunderstorms are big enough and massive enough and persistent enough to actually influence the jet stream coming off of the Asian continent. So the North Pacific jet is responding to where those thunderstorms are. Those thunderstorms, though, can move. And in an El Nino event, the warm water fills in back towards the east. Those thunderstorms come towards the date line, sometimes comes closer to South America. And as they do that, the jet stream starts to respond, and the storm track drops towards us, okay? So in an El Nino event, you end up having a pronounced storm track that persists across the southern part of the country. And you can get parades of storms from Southern California all the way to Florida, and we can get lined up in them. And they're great winners, okay? They're a little finicky, though, and I'll show you what the finickiness part of it is. The other side of the southern oscillation, the La Nina side of the El Nino southern oscillation, is where we end up having the storm track move north of us. Okay, so it's the opposite pattern in the Pacific. Cooler water in the eastern Pacific. You got to do all this visualization now, and you have to start thinking about the globe in your mind here. Cooler water in the eastern Pacific, much warmer water in the western Pacific. Jet stream responds. We get a wave in the jet stream that becomes fairly pronounced, and the storm track ends up riding north. We're underneath a high pressure system. We have beautiful, sunny weather all winter long. It's warm, it's pleasant. It's not raining though, right? Pacific, the Pacific Northwest is getting Seattle weather like on overdrive. Just raining all the time. All the time, all the time, all the time. So it gets much wetter than average during a La Nina winter in the Pacific Northwest, drier than average down here, okay? So you can envision when we have these slow changes in the Pacific, they can set up in the summertime. And in the summertime, you can see a La Nina or an El Nino event, and you can say, from a forecasting standpoint, I expect next winter, months away, to be warmer or drier for Arizona. And that's how we do seasonal forecasting. And I'll show you a little bit of that. It's not perfect, though. You may have already gathered that. La Nina events, though, are reliably dry for Arizona. So if we have a La Nina event developing, it's a really good chance it's going to be a dry winter for Arizona. If we see an El Nino event coming, we can lean towards wet, but they don't always work out that way. Okay, so this is Saturday morning. You're spending your valuable time just looking at scatter plots, and they're going to get much worse. I'm just going to tell you, they're going to get much worse. Okay, so this is data for Yavapai County. It's Climate Division 3 from 1950 to 2018. And I took the winter time, December, January, February, total precip for each of these years from 1950 to 2018. And that's organized on this axis. And then I plotted it with the strength of an El Nino index. Okay, so the red dots are El Nino events of increasing strength. The green dots are where we're in normal or neutral conditions across the Pacific Ocean, so neither a strong El Nino or La Nina signal. The blue dots are La Nina events of increasing strength towards this axis. So over here are the strongest La Nina events of the last 68 years, the strongest El Nino events of that same time period. Okay, so if you remember your statistics, when you plot, do you remember? Everybody's like laughing now. Okay, so in this scatter plot, if there's a relationship between two variables, they will start to organize along an axis, okay? If it's a cloud of points, then there's no relationship, okay? And you can calculate something called the correlation coefficient of 0.38 is the correlation coefficient, and so we draw the line through there. It's not a very good correlation. It's not, in my line of work, it's not bad, right? Economists and climatologists, we're the same. We are the same. We do the exact same statistics, too. It's funny. When I hang out with economist colleagues, we have very low bar for success. So that is that's what you see here. I go, oh, yeah, that's not so bad. It's not great, okay? Actually, the explained variance is if you square that value, you're like about 10% of the variance. So what that's basically saying is that around this line of a relationship saying that El Niños are wetter and La Niñas are drier, there's a lot of spread. There's a lot of other possibility there. Okay, but there's still something here. This is actually significant. There's a real relationship here, but it's noisy, all right? Still there. So if we look here in La Niñas, and again, think about what this says, is that we know these events occur over seasons, so they are slowly evolving, and if they're evolving in the summer, we can anticipate how things might turn out in the winter. That's really fascinating. That's a forecasting tool. So if we have a La Nina event occurring, those events historically have been on the dry side. Not all of them. This is the long-term average for winter for December, January, February. There's a handful above, but a lot of them are below. There's a lot of overplotting here, but 2018 is right here. So it was pretty true to itself in being a La Nina event. Okay. Does anybody see 2016? The Godzilla El Nino? You can't see it. It's so, yeah, that was disappointing. That was where we had to go back to the drawing board. I was forecasting 2016, which was the strongest in the last 68 years, this El Nino event, to be with its siblings of 1983 and 1998, and it wasn't, right? So it wasn't. So it's imperfect, but it's still, there's something here, and we had to go back to the drawing board to try to understand what that is. Okay, but if you look around here, that's okay. There's 1993, which I'm sure you all remember or have thought about or have seen the evidence of it, was a neutral winter. It was not an El Nino winter. It's often called an El Nino winter. It wasn't. That was not what was driving that. It was atmospheric rivers, which you hear about in California now, came through Arizona, rain on snow event. Okay? And then 2004, 2005, right here, and that was a weak El Nino event, not unlike what we're seeing this year. So El Nino is there, but it's probably not doing much. It's probably weather. Normal variability, weather scale variability, driving the variability we're seeing right now. Okay, so this is your envelope of El Nino forcing, El Nino, La Nina forcing that wintertime variability that we see here. Okay.
Where does the index come from?
The index is a measure of sea surface temperatures across a part of the Pacific Ocean, and if they're warmer than average, this index is positive, and if they're cooler than average, the index is negative. That was a good question. Okay, I should also say the monsoon is pretty agnostic to El Nino and La Nina. It doesn't really care. There's some weak evidence that La Nina events draw in an earlier monsoon and El Ninos suppress it, maybe cause it to occur later, but it hasn't really borne out. We do the stats, and then 5 years play out, and they don't hang with the stats. The stats fall apart. And then dynamically, we can't even model it. So it's pretty messy. So really, when we think about El Nino, La Nina, we're thinking about the wintertime here in Arizona. Okay, all right, totally out of my wheelhouse here, but I love this graph. I used this graph back, I think, the last time I was here, and I found it in my old slides. And I just encourage you to go play with this. So this is a graph of stream flows on the Verde below Tango Creek. This map doesn't really help you too much. But I wanted to point out that what I was talking about as far as this spread of variability shows up really nicely in the stream flows, the seasonality of the stream flows on the Verde. You can plot this at USGS WaterWatch, really nice tool. And what it is it's the daily stream flow. So there's a little, these look like these little DNA strips or tests right here, but each one of these little bars here of color is a daily stream flow value, and they're plotted for every day of the year, through the year, this direction, and so they wrap around. So they keep repeating. So this is a continuous daily stream flow record from, I think this is 1945 or something like that, all the way up to 2010, and I'll show you the updated version as well. But I wanted to show you again, so this is the broad variability in hydroclimate here is this season. This is the dry spring here, the decline in stream flows. This is the reliable monsoon, but interestingly, it does not have as high of values on the stream flow side as the winter. So we're already starting to see that high variability in the wintertime season is a little bit different because it's happening during a cooler season, and so it can soak up a little bit of that variability over the long melt and recharging of soil moisture that you get here. But if you look at this axis, there's still that kind of up and down of dry periods. Here's the wet periods of the 80s. Some high flows in the 90s here. More recently, a dry period. This is actually an El Nino event right here. There's one event, I actually wrote a paper on this in particular. I was really interested in this, but there was a record dry winter in 1971-72 water year. You can see it right here, these real deep dark reds. We wrap around. This was the dry winter right here. Right here, this is October. Two tropical storms and then a winter storm over 2 weeks pushed up the stream flow, and that stream flow signal ran into an El Nino year, and then you end up having elevated stream flows all the way through. There wasn't a dry down in spring. It wrapped all the way around to the next year. So these little odd sequences of these seasons working together, which are completely unpredictable, can drive these short-term wet periods, okay? They're nothing you can count on, but they're really interesting when they do show up. Okay, so this is just updating it to the last, from 2010, the end of that graph, to present here. But you do notice something kind of interesting here too. So there's some of those winter wet seasons. Again, this is an El Nino event that showed up late in, if anybody remembers this, in 2010, Flagstaff got 10 feet of snow, and there were flooding in Gila County, a tornado in Scottsdale. It was and it was over a 2-week period in January, and then that was it. And so you went from very wet to very dry conditions. It got very warm here and very dry, and then the Schultz fire occurred in Flagstaff. And so they went from record snowfall to a fire in town in 3 months. So that's Arizona right there. That's tough to pull off a lot of other places. Okay, but you also notice this too, is that this kind of drying signal starts to creep wider over the last decade. Okay, so that is precipitation, maybe some of that temperature aspect as well, creeping into it. And then here's right now, this is that event of just last weekend that pushed everything up. We had rain on snow event pushing up the flows. And you can look back, not unprecedented, in January or February over the last at least 10 years. Okay. Great. Okay, so try to pick up my pace here a little bit. I wanted to kind of walk back through last year, because I think last year's a really good case study on the weather timescales of what can happen in Arizona. All right, so right now, if you're paying attention to the U.S. Drought Monitor, it's a lot better in Arizona very quickly. And that was, if we go back to last October of 2017, we weren't too bad. We came off a pretty good summer. We then moved into a very dry winter, record warm, record dry October, November, December, and not a lot going on. We'll actually look at that a little more closely. So drought conditions really crept in. And then by right before the monsoon signal, we actually started to have, this is exceptional drought conditions, so there's a 1 in 50-year drought conditions creep into much of the central part of the state. Okay, so it had gotten that bad that fast because of that combination of record dry and record warm pushed the drought monitor expansion very, very quickly. And so to whipsaw us back in the other direction, we're now, if you look at the end of October, you get this very strange looking drought map. Does anybody know what this kind of strange, this is? So this is low drought conditions, abnormally dry. That was Hurricane Rosa that went right up the middle part of the state in October, and it was 5 to 7 inches of rain in a day, 2 days, 3-day totals. So it's really hard, it was hard for the drought monitors to hold on to drought conditions in that situation with all that rain. That's the real tough part about doing drought here in Arizona, is you're constantly following the laser dot of weather back and forth, extreme here, extreme there, extreme here, extreme there. I argue that we can actually have drought occurring and not drought occurring at the same time, depending on what you're talking about. I know, it feels like I can have it both ways. That's what I'm going for here. I sound like an economist. That's exactly right. Exactly right. The recovery is in effect, but it's really bad out there. So I want to, yeah, exactly. That's right. All right. Okay, so, but we'll pick that apart a little bit more about how we can have both at the same time. All right, so this is a map of February through January precipitations. This is all the way up through just a couple weeks ago. So the 12-month total from February to January of last year, remember, includes a dry period and a wet period. So when you mash those together, you get average. It's kind of unsatisfying, right? You have two extremes, you average them together, and you get blah. And that's what we end up having here. Temperature-wise, pretty solid, much above normal. If you go back to last winter, for a couple of months, it was the record warmest in the last 120 years. Okay, so let's take Prescott, the Prescott co-op station data here. These are some plots that I pull up. And so this is October 1st of 2017. We're gonna move through and look at the weather scale events. So all that happened last October 2017 through May 31st of 2018 was it rained 16 days for a total of 2 1/3 inches, and it was like middle of January, an event almost an inch, and then some kind of spitting here in February, an event in May, which was a cold event if I remember correctly. But this deficit, you should have been here up over 9 inches. You ended this 8-month period with just a little over 2. So it was the driest October through May on record from 1962 to 2018, and the third warmest. Okay, so if it stood out as unusual to you, you weren't making it up. It was a crazy warm and dry winter, and was La Nina driven. That was really the culprit for that. Shifted storm track. This was monsoon season of 2018, last monsoon season, and a real breath of fresh air, so to speak. If it's monsoon season humidity, strong, frequent monsoon activity in July, fairly frequent through August, and then it really dropped off out here. It was a little bit busier to the south in Tucson, but ended up being 12.2 inches. It was the 9th wettest on record, and it was the 7th warmest as well. So it didn't necessarily cool off, still very warm, but wet. And I'm sure you were happy about it, as we all were. I was really worried about the fire season by the end of May, and really feel like we dodged a bullet and needed the monsoon to come in, settle in a strong way, and it did. Okay, so this is what's happened since the end of the monsoon, so October 1st, right up into a couple days ago. It's been interesting. It's been a weird mixed bag. We had a busy October, tropical storms, and again, that moisture, you can't rely on it from year to year, but when you get it, it's a really good thing. So that to me is a little bit of a distraction, but I think it's certainly beneficial. November was dry. December was fairly warm and dry up until right around the holidays. We got into the holidays, we had a very nice, in the long-term average perspective, a normal-ish Arizona winter. Cold, wet storms with low snow levels came into the later part of December and the early part of January and brought some beneficial precip. And then more recently, we've gotten warm, wet storms. And interestingly, El Nino is in the Pacific, but has been useless. It hasn't done anything for us. It has, though, yielded its way to something called the Madden-Julian oscillation, which are pulses of tropical convection that come across the Pacific and go all the way around the world at the equator. And as they come by us, they tend to enhance the storm track and bring flooding rains to California. And if we're lucky, we get in on the action too. And that's happened. That happened last weekend, and it looks to happen next weekend as well. So good, all right? So that's kind of the weather scale, time scale variability of what we've seen here. Okay, so, and again, apologies. This is a terribly abusive graph, but this is where I get to have it both ways. And I want to articulate, we have all these short-term rain events, pulses, which are weather, and you have to start thinking at climate timescales, and you have to think of climate timescales at increasing lengths, all right? So this is a graph. I take the data from Yavapai County, and I go back to, this is from 1981 to 2018, and I'm going to calculate a drought index on these data, these monthly precipitation data, which are down here. So the green bars are above average for the month, brown are below average for the month. So you can see wet periods, dry periods, more pronounced dry periods. And these drought indices, each one of these, there's a little square here, which is a month. And I will take an average for 1 month, 2 months, 3 months going backwards. And so I'll bring the past up into the present. And it's a moving average to make sure we don't forget about previous drought conditions, and we move it forward with us. Okay, so if you are thinking about monthly precipitation, it's either up or down or up or down or up or down, right? But then we lose track of, was last summer dry or wet? Was last winter dry or wet? Were the last 3 years dry or wet? This helps us do that. So this is, on this axis, is increasing time scales of drought, and on this axis is through time. All right, so if we look at the data through the end of November, we can see the 1 month drought index is near average. If we look at the last, so this is 5 to 10 months, we're going to take in the summer, and the summer is actually going to swamp out the previous dry period a little bit here, and we're going to get near average. But if we go out to longer time scales, say 2 years, we get drought to come back in. And as we go out to longer time scales, you get a little mix of drought, a little mix of wet conditions. But what you can see over time here is that the slowly evolving part of climate variability is up here. So you get wet periods, dry periods, wet periods, dry periods. This is the very dry period of 2002 drought. You can see it really showing up here, smearing into the future here. This is the wet period of 2004, 2005, that winter. And then the more recent drought period. And down here we have noisy, seasonal, gets better, gets worse, gets better. But you keep your eye on the longer term. We really have been in pronounced, protracted long-term drought since the 90s. We haven't had a sustained summer season, winter season, summer season, winter season above average precip since the 80s. Right? So to get to that longer-term drought recovery, you need to do back-to-backs. You need to get your seasons to work together and produce above-average precip. We just have this mess of it's good, it's bad, it's good, it's bad, it's good, it's bad, and it cancels each other out. All right, and it's getting warmer. All right, so this gives you your longer-term drought, and when we think about water, it really starts to, when we talk about the integration across a basin, is the longer-term climate variability is what we're looking at. That point. You can have instantaneous floods, but the longer-term climate variability is going to be what's going to drive the slower varying aspects of stream flow and groundwater. Okay, so then we can look at this over long periods of time, still taking that Verde-Salt average. So each of these years, this is calendar year total precip, 1895 to 2018, and it shows then the basin-wide average. Sorry, this should be verti-salt. So the verti-salt average is around 21 inches for the calendar year. So it's the highest and lowest elevations, all averaged to one number. So what this helps us do is look backwards to see that decadal variability. Okay, and so if you follow this line right here, which is the 10-year moving average, here is a wet period, a dry period, a wet period, a dry period. And it has decades of swinging up, decades swinging down, same here, same there. But you notice in those decades you have wet years and dry years, right? Okay, so that's where you can get a little bit distracted and not have your eye on the ball of the longer term variability. Okay, so this we call decadal variability, largely related to El Nino, La Nina, stacking up over decades of becoming more frequent El Nino or more frequent La Nina. So the 50s drought, one of the driest years in record, 1956, is kind of in the heart of this period where there were more frequent La Nina winters than neutral or El Ninos, leading to drier conditions over a longer period of time. If you look at the tree ring records, you see this going back 1,000 years. Okay, so that same slower varying, noisy, but slower varying component of climate. You can see your 2018 right here. So definitely in the middle of a drought period. Middle, end, front, first period of a third period, 3-period hockey game? I don't know. That's the real $1 million question, right? We have droughts in the tree ring record 40, 50 years. We also have ones that are 20 years. So I can't tell you. I know everybody wants me, so make a guess. No way. I've done this long enough. Yeah. So no, that's not a good idea. Okay, so we can rescale this graph. This draws it out a little bit more. These are the drought indices, so it's difference from average. This would be average. You can see here, we don't spend a lot of time near average. We do a lot of sort of cycling up, cycling down, cycling up, cycling down. The last 20 years here has been noisy, but generally drier than average, winter upon winter. This is calendar year too, so it also lumps in that monsoon signal. Okay. This is a graph I showed many years ago. It's from a 2005 USGS report, and it really kind of links back to that decadal variability. The orange bars are sort of pronounced periods of below average stream flows, blue bars above average. So you can see drought periods, wet periods, pluvials in the climate language here, and then this more recent drought period here. So really strongly tied to longer term variability related to El Nino and La Nina. Okay, so this is all happening at the same time that temperature is doing this. Okay, so this is for the verti-salt average calendar year temperature from 1895 to present. Okay, so it is not doing decadal variability. There is variability in it, but there's largely trend in the last 50 years here, which can't be explained by changing sea surface temperature patterns or cyclical variability in that. So this is the climate change signal come home, and you can see real pronounced warming over the last couple of years. If you do the water year, October of 2018 through, October 2017 through September of 2019, 2018 is the warmest year on record by using that grouping of months. Okay, so we can think about the interactions between precip and temperature by combining them through drought indices like this, which is the standardized precipitation minus evapotranspiration index. I'm going to talk a little bit more about evapotranspiration, but the inputs to the system with precip, in a very simple way we can think about the outputs or the forcing on the system is evaporation and transpiration, right? So as it gets warmer, evaporation goes up and transpiration, the water used by plants, goes up too. So those potentials go up and want more water from the system. And so a water balance where you end up having as much rain come in as leaves through PET is balanced. And anything where it's imbalanced, where there's not enough precip to meet evapotranspiration, is an arid climate. Okay, so in Tucson, the average precip is about 11 inches for the year. The average potential evapotranspiration is about 70 inches. okay? So that's an area, the plants that grow there natively know that, right? Cacti are really good at using water. They can get by in 11 inches when the atmosphere wants 70, right? So it's all about those landscapes and having the adaptations in play. But as temperature moves along, all of the water balances locally respond and change to having warmer conditions. And we'll look a little bit more at that. But this drought index then takes that water balance, and you can look at the 50s drought and compare it to the most recent. This is a warmer drought, so it is now worse than the 50s drought through the additive effect of having higher temperatures, okay? This is clunky and not very nuanced and somewhat imperfect, but at least is leading us in a way of thinking about this. Is this the exact water balance that's occurring in the Verde Salt? No, it's way more complicated. But at least starts getting us to think about where the water is and if the water is going to be there under the same amount of precipitation. Okay, so to this point, increasing temps, increasing potential evapotranspiration, increasing aridity. Okay, so that's just very simple. You go to Yuma, it's different than Prescott. Nobody's going to argue with me on that, okay? That's an extreme example of having low precipitation, high temperatures, and then a subtle shift in that water balance. Not so subtle. It's much cooler here, much wetter than Yuma, right? So that on a long-term scale is going to give you different levels of aridity. All right, so on average over time, again, in climate timescales, years to decades, shifts in temperature will shift water balance. In a given year, it's real tough to look at the component of temperature driving where the water balance is. We're just not sophisticated enough to do that. But over decades, you can absolutely say it's much warmer now, so the water balance indeed should have shifted in response to having those warmer temperatures. Okay, so precip needs to increase to meet increasing PET for the water balance to stay the same. So as it gets warmer, it needs to rain more here to not have the water balance shift. Okay, so that's another thing that we have to keep our eye on in this whole discussion here. But again, I don't want to oversell that it's this simple. On average, over long periods of time, it does average out to being this simple. But in a given year, an October rain can make a huge difference in the water balance for the year, right? And this is where we aren't real great at tracking water balances at that fine time scale and incorporating all the weather scale events. But we can't rely on the vagaries of weather to counteract the long-term trend of the shifting water balance. Okay, so another scatter plot. You guys are all trained up on these, right? Okay. What you may notice here is there is indeed, this is the January through December potential evapotranspiration here. I'm sorry, I think I got these wrong. Here, monthly average potential evapotranspiration. So times this by 12 to get the annual total. I'm sorry this plot doesn't already do that. And this is the annual total precipitation. Just to make the point that the 80s, these gray dots, 79 through 91, were a cooler, wetter time. 90s through 2004, these kind of pink dots here, they kind of span from wet to dry. And then the most recent sort of 15 years or so is here, which are their drier conditions, higher levels of evapotranspiration, and also drier on that end. So it's not pure attribution. It's not drier now because it's just warmer, and not vice versa. So it's drier now because it's not raining as much, but it also additively is also warmer now too, right? And right now, most of that variability is controlled by the drought signal with some added temperature forcing on top of it. It's not all temperature right now, but it could be in the future. Okay, so the dark arts of seasonal forecasting. This is what we're looking at from the Climate Prediction Center. March, April, May, upcoming March, April, May, all the way through next summer. The green is a lean towards that 3-month period being wetter than average. And you can see Arizona is mostly in white. White means equal chances of below average or above average precip. What you going to bet on? They bet on none of them. So that is an equal chances forecast. Low confidence, no confidence, basically. No confidence in making a call on any of those categories. So it's a shrug. We're not sure it's going to happen for the rest of the spring because El Nino never really showed up in earnest. We can look out here to the summer. If there was a forecast, I wouldn't believe it, but there isn't, so that I believe that. So we don't know. So I believe that that's right. Yeah. Okay, so the seasonal temperature outlooks, though, do in the spring start to lean above average, and then they go to a pretty strong confidence in above average temperatures for the summer. That is trend. They know it'll be warmer this summer because it's always warmer. The forecast is now made on the trend. It's not, there's no fancy really weather modeling going into it. It's just trend. It's above average now. It was above average for the last 5 years. There's no reason to believe it would be below average this upcoming summer, so it's trend. So that forecast is there. So you can start doing the mental modeling here of saying, good winter, it's going to warm up again though, so where does the water go? Probably back into the atmosphere, right? On longer term averages. Okay, the real dark arts now are climate projections. And I want to point out that this is a graph from the latest National Climate Assessment. And I like it. It's a little hard to explain, but I want to point out that the time scale that we're looking at from present out to the end of the century and the data that are presented are a mess of confidence and uncertainty in different aspects of our science, okay? So at short time scales in the order of seasons, as we just looked at, most of our uncertainty is in internal variability, which is El Nino, La Nina, Madden-Julian oscillation, the shorter term sort of seasonal aspects of varying climate. So at shorter time scales, we have scientific uncertainty and uncertainty in how that will evolve to do good seasonal forecasting. So that's why we don't really know what will happen next summer, because there's a lot of this. Okay, so the climate change component is this scenario uncertainty, which is the aspect of greenhouse gas changes enforcing on or uncertainty. And so you can see at the decades time scales, that aspect is small relative to the uncertainty of the complexity of the climate system, okay? So when you want to know from climate scientists what's going to happen in the next 10 to 20 years, you're asking the hardest question, and if you get a certain answer from somebody, turn around at that point, because that's the hardest part of the system to understand. Okay, so when you get out, though, at the end of the century, the scenario uncertainty, which is the aspect of the greenhouse gas changes, carbon dioxide, nitrous oxide, methane, become much bigger parts of the uncertainty. And this is policy changes, whether or not there'll be big changes, either up or down in those, start to become more important in the confidence of those projections than the variability here, right? So this is a little bit of sort of like best practices in sort of thinking about this information, okay? And so when we start to think about a projection at the end of the century, we're really starting to have our head around, well, what were the policy changes that have occurred in between? And that's where you have hope, because this is the aspect that you have control over from a policy standpoint, right? We don't have to control the weather here. This is what we're talking about here, right? Which is not a good strategy. Here actually puts us into a good policy discussion. Okay, and so when we look at climate models on the scenario side, these scenarios are projections of greenhouse gas changes from now until the end of the century. And you'll hear things like RCP, relative concentration pathway, and they are varying pathways on levels of emissions over time. And so RCP 8.5 is the high-end emissions scenario, and that's 8.5 watts per meter squared, if you really want to know, of additional forcing on the planet. So it's 8.5 additional watts of incoming radiation or downwelling radiation every square meter. So it'd be like 8 old Christmas lights added to every square meter of the planet. That's the extra energy. at the end of the century. So it's a lot. So it's a lot of forcing. 4.5, and you'll often see the models give you 8.5 and 4.5. 4.5 is a solution where the policy changes come into play, and emissions stabilize and then become negative, and we start to go down. So you can see this blue line here, and this 8.5 right now. Okay, so what I'm going to show you is just worst case scenario, not because I'm a glutton for punishment, but more of it's a good planning tool to give you the high-end estimates of the information. And this is a really excellent toolbox a colleague of mine at University of Idaho put together, the climate toolbox, and you can go in here and get more information than you ever want, but you can get local, your backyard climate projections for what it's worth. And that's what I did here was I dropped the pin on Prescott, and it gives you in decades changes in warmest temperatures, average high and average low. And so by the end of the century, under RCP 8.5, it's 10 degrees warmer in Prescott than it is in the previous decade. Okay, so it's a lot warmer. And then your hottest temps become closer to 107 where they were prior 97. Okay, so it's a 10-degree warming. It's a lot of extra temperature to deal with. Water balance-wise, the annual average precip, though, look at this, 19, 20, 20, 21. It doesn't change much. That's what the models are suggesting. The models are suggesting decadal variability going into the future under warming conditions. Okay, so there's no real model consensus of it getting drier, less precip here, and warmer. It's crazy weather variability continuing under warmer conditions, right? So this is, I think, a thinking that we've got to get our heads around, is that we will have wet periods in the future, but they'll be warmer, right? Those will be really tricky periods to keep attention, right? Because under those conditions, it'll be wetter, but it'll be warmer, so where's the water going? I don't know. Probably not where we thought it was going, right? And so those will be the wet periods to really make sure that we're not distracted. The water deficit is down here, 40 inches to 51, so an extra 10 inches of deficit by the end of the century. That's that point of even under constant precip into the future, warming conditions lead to an extra deficit. All right, here's just more of the same. This is for Prescott. This is historical modeled into the future. This is the spread of the model, annual average temperatures. So a shift of just about 10 degrees from the historical record to the projections. And then precip, here it is again. See how the distribution of the models gets wider? That's uncertainty, right? It could get wetter in the future in a season, subtle shifts. The models are all over the place on that, but it'll be under warmer conditions. This is where I feel like I go off the rails. I'm not suggesting it's going to get wetter and everything will be okay. I'm suggesting that the variability down here is crazy, and it's hard to anticipate what from decade to decade it is. We will get into a decade, though, where it'll even out to about average, maybe above average, but it'll be warmer, right? And those are the decades that'll be really tricky for us to get through because we will think it's okay, and it might not be. Okay, so there's that potential of evapotranspiration getting higher. Okay, I went in and actually pulled some data for the Verde, and I picked a warm dry model. So the models, there are over 30 models, different universities and research institutions all over the world, all have slightly different results. We end up averaging them together to try to get a consensus on that, an ensemble mean. We have some known dry and wet ones for the Southwest. One is the Hadley, one is the CNRM, and I pulled them for the future, and it was interesting to see. So this is for the whole Verde, the average annual precipitation for the Verde through time. This ends in 2100. Each of these little box plots is the monthly distribution of precip within that particular year. And what I gathered from this is still the same kind of ups and downs and ups and downs and ups and downs and ups and downs, right? It looks like the past because the models are latching on to that same variability continuing in the future. They might be wrong. That's totally possible. We might not have El Nino worked out. That's probably true. There's some other subtle things like tropical storm activity, but for right now, that decadal variability continues into the projection space. But the temperatures go up. And the warmer, drier is on the high end here, the Hadley model, and then this is the cooler one. So the cooler one does not give us another outcome that doesn't have the warming. The cooler one is just slightly cooler. Okay, so to wrap it up, oh man, I really went slowly here. Okay, so this is kind of that background creeping crud of the climate in the high variability southwest here. The subtle shifts, and it's really a problem up north, is that changes in snowmelt mean changes in hydrology, and our management systems around reservoirs have to change. Our thinking has to change. We're all living that in the state right now. And that background warming leads to changes in the snow water equivalent on April 1st, and then the subsequent runoff that we can expect over the springtime season. And real huge concerns up here, but certainly a concern for Arizona as well. All right, wrap it up and I'll take some questions. Closing points, complex hydroclimatic variability, I keep saying that over and over again. Lots of time scales, leads to high levels of interannual variability. The climate models project similar, if not higher, variability in the future, maybe some wider guardrails to crash into from year to year. It's definitely possible. They also have higher uncertainty. I think the sort of it moving forward as the variability will be similar, I think is reasonable at this point. It's going to get warmer. It's going to continue to get warmer decade after decade. And then having those two things will lead to shifts in the water balance. And can precip keep up? On average, over time, probably not. In some years, probably yes. Right? That's the interesting thing about these. If you get a wet year from month, beginning of the year to the end of the year, and it was cool, you will see some change, positive change in water. But then what's the next year going to look like? You could erase that pretty quickly. And we've even seen that over the last couple of years. We get more of last year's stacking up on top of each other. You get into trouble quick. If we can do this winter and stretch it out with another October, we buy ourselves a little bit of time. So that's that precip hydroclimate side of it as stuff gets warmer in the background. Okay, thank you. Well, you really hung in there. I really appreciate it.
Okay, thank you. So let's have a few questions. I know John Zambrano had a question to start with.
Thank you for the talk, Mike. It was really, really enjoyable.
Good.
A couple of years ago, I wrote you about the fact that scientists nowadays seem to be willing to attribute particular extreme storm events or rain events or hot weather, bad weather to climate change.
Yes.
You came back and described the issue of attribution. Can you elaborate a little bit on that and explain to the audience?
Sure. So attribution is a pretty young part of climate science where models are used to look at recent extreme events and try to partition the components of natural variability versus climate change on their occurrence, right? And so what you can do is you can look at events like Hurricane Sandy, Hurricane Harvey, flooding events in different parts of the world, drought events, and you can then run the model and try to recreate that extreme with greenhouse gases and without. And so, and you do this in model space, and you do 10,000 models, and you come up with a distribution, and then you look at shifts in the probability of that event occurring with climate change occurring and without it. And then you can make some probabilistic assessment of whether or not this event was more likely to happen with these greenhouse gases or not. And so there have been a lot of interesting things. So the drought, there's a paper on the drought of 2010, 2011, which largely ascribed, that was the drought from Texas all the way across to us. That drought was largely ascribed to natural variability. That was a La Nina-driven drought with a little bit of added enhancement from it being warmer, causing drying, but largely natural variability. Hurricanes, I can't remember the Hurricane Sandy, but Hurricane Harvey had an attribution where it certainly could have happened under a climate system without greenhouse gases, but the subtle enhancement of having more water vapor in the atmosphere caused the rainfall amounts or totals to be slightly higher than they would have been without, right? So you start to parse a little bit, but you start to see leans, and there's a spectrum of things that you can attribute, right? Changes in pH in the ocean are, you can't attribute that to anything other than carbon dioxide being dissolved in the ocean and changing the pH. All the way to that event last week, was that climate change? It's not even the right question at that point. That's a weather scale event that would be hard to make sense of. And then you got everything in between, where longer scale, time at climate scale, you can start to see shifts in the frequency and the probability of those events.
So, next question. Let's see. Who had their hand up in here? Dave?
I have two questions. When you say dramatic increases, what are you talking about? 1/10 of a degree or 2 degrees?
So these would be these temperatures right here.
I can't read that.
Oh, I'm sorry. Okay, so this is the 2000s historical record. About 85 is the summer average temperature for Prescott. 2085 is 95.
Oh, I see.
So about 10 degrees.
Okay, thank you.
Yeah, and any kind of these graphs about 10 degrees.
One more question
Yes.
about one of your more recent slides. You were
Yeah.
talking about a number of studies worldwide,
Mhm.
correct? That were all over the place?
On monsoon
Models.
models, monsoon precipitation. Yes, monsoon season precipitation.
Okay, and the result was that all of those widely varying results were averaged?
Yeah, that's right. So that's this. You see how this line is flat?
Well, it was a previous slide to that.
No, this is, the projections are here.
Well, go ahead. There.
This one? Oh, okay. These are individual models. So this is not the, this is actually diving into two different individual models.
Maybe that's not what you had mentioned. Your verbal,
Yeah.
that you had averaged a great number of models
Yes.
that were all over the place.
Yes.
Okay. Is that what a scientist would do, or did you start realizing that if models are all over the place, maybe none of them are right?
Well, so okay, so that's a good point. Maybe I was a little bit too grumpy about models. So models are useful tools in as much as they help us understand how things fit together and representations of reality, right? So these two things show us temperature changes in the historical record and changes in the, temperature in the historical record and precipitation in the historical record. What we know when we do model evaluation studies across all those models, and we focus on the Southwest. I was on a grad students committee who did this for the monsoon. She found that some models got the seasonality of precipitation closer than others, and then some of the models didn't even do the monsoon right at all, right? So to your point, there are a subset of models that should be used for looking into the future, right? This is actually, you've touched on the debate in climate science.
In a sentence,
Yeah.
my point is, aren't you averaging in bad data?
Yes, yeah, for this. But what we see on the precip side, you do get bad data in with good data, but on the temperature side, they're all doing the same thing. The point is that in historical attribution studies with temperature, the models actually do a good job. In the historical attribution with precip, they don't, because down here for the Southwest, they're not getting El Nino quite right and they're not getting the monsoon quite right. Some models do better than others. And you've touched on a point. There are papers now on, is the ensemble average, meaning all those models averaged together, useful? Or should we be picking out select models and using those? Yes. So the results are mixed, and it depends on your question, the season you're studying, and if it's temperature versus precip. If it's temperature, the studies all come back and say average them together because they're good enough and they're tight enough and they're contributing additional information to each other. On precip, I'm with you. That's where we go into things like this, where I dove into the individual models, and if we look historically, we know that the Hadley model, funny enough, the Hadley Center out of the UK does a decent job with the monsoon. And so some of the studies for the Southwest on climate projections are using the Hadley Center model for trying to see what changes will be like in the future.
Are they the hockey stick center?
No. That's a different research group. Yeah. No, this is interesting. The Hadley cell, part of the UK Met, has come up with a really good model that they're using on seasonal timescales out into projection space as well. Yeah.
Get this mic on. There we go.
Rainfall data collection.
Yeah.
My turn next. Again, on the idea of the different great events, one of the things I've been curious about is forest fire.
Yeah.
Because there's a lot more coming, and I'm curious to know what effect precip and temperature, because it's going to affect both of them depending on the amount of particulate, I'm assuming.
Okay, so the change on the ground increasing forest fire risk, or vice versa, or the increase of forest fires causing more climate change? Okay, so there has been evidence over the last couple of decades that the increase in forest fire has increased the flux of carbon dioxide into the atmosphere, and a lot of those have been fires in Siberia. I don't know if you've heard of, they've had 10 million acre fires over the last, it's global, right. And certainly in the West, that's a case too. Particulates have a strange effect where they actually can cool the environment. So if you have a smoky summer, you actually end up having less solar radiation make it to the surface, and it cools slightly. So it can actually counteract the warming that occurs with them at the expense of human health, for sure. Right.
So, another question right here.
Thank you. Rainfall gauging around here is a curiosity to me because the city and NOAA rely upon the master gauge at Sundog.
Yeah.
And Sundog will record 5/10 of an inch, and hell, I'll get 2 inches in my backyard.
Yeah.
So what is that? What's causing that?
It's the spatial variability, and you're probably getting that in the summertime primarily, right? Okay, so the character of monsoon storms is different. So the wintertime is going to be primarily frontal and orographic. And so it's going to be large waves that come off of the coast of California. There'll be broad areas of precipitation enhanced locally by being driven up topography. So you look spatially, the precip amounts will hang together better. The summertime, this is the cool thing about Arizona climate, is that you've got these two different mechanisms with each season. The summertime, it's all thunderstorms. It's not frontal. And the thunderstorms are driven by the mountains. If you ever look at the satellite picture in the afternoon in the summertime, it's just all these little cauliflowers on the tops of the highest peaks, right? So that's driving that. And then they will, if there's enough wind, they'll move off in different directions. They will cause outflows. They will cause other storms to form in an erratic, like billiard ball fashion. You know, they'll just kind of move off in every direction. So it's unpredictable in that sense. And then you can end up having 2 inches at your house and 3 doors down. They won't have anything, right? I'm doing a study. So I also run RainLog, which I'm sure a lot of you probably are doing RainLog. We're now digging into the 15 years of data, and we're looking at some of that spatial variability in some of the areas. And just in Tucson, it's enormous. It's enormous in one contiguous city on the different monsoons that people can have. I had twice as much rain on the east side of Tucson as a colleague near campus, and it's flat. So that to me was fascinating in that. That's another really crazy thing about climate going forward. Yes?
I'm just curious about the effect of temperature in other parts of the state. You indicated that there's a 10-degree increase over time in Prescott.
Yeah.
Is there a 10 or more degree or less degree in Phoenix or in Tucson?
It's primarily uniform. If you looked at the projections going forward, you'd basically add 10 degrees Fahrenheit at this high emission scenario concentration to all of the annual temperatures across the state. So you'd take Tucson's summer temps and you'd add 10 to it, and you do the same for Flagstaff. So there isn't much spatial variability in the warming. On the continental scale, the coast warms slower than the interior because of the moderating effect of the ocean. That's what you see pattern-wise.
Can we conclude that as the temperatures get warmer and evapotranspiration increases, that whatever aquifer recharge we've been getting will decrease?
See, I already warned people that as soon as it hit the ground, I don't know where it goes, right? And that I always get that question. I did this in the Gila watershed. They had the same question. I knew they were going to have that question. I don't know. I mean, again, Bill and I were talking earlier. If the water falls on the ground and it doesn't run off and move quickly away and out, and then is in the root zone, if the roots take it out of the soil, then it's gone. If it makes it past the root zone, then I think gravity takes over, right? So it goes down, right? So then it really becomes a matter of how often those events are occurring, what the background evapotranspiration is. So the frequency, background of evapotranspiration, and amounts over time, right? And then, but then you got to start to think about a basin, and it's rock and topography and soil. I mean, that's where I just like lose it. I can't even think about it at that point. Like, I can barely get my head around this stuff, and then I really feel for you when you start to like, that's where all ever Arizona is, right? We get to this point, and then we're tracking every drop of water and where it's going, and it's really, really hard at that point. I did not answer your question. And that was right.
Michael, I've got one quick question
Okay.
for you. The terms drought versus aridification, am I correct in saying that drought carries with it the implication this is a temporary,
Yes.
i.e. a weather,
Right.
and aridification would refer to a climate change, a longer-term change?
You answered the question really well. So droughts end. They can't be droughts if they don't end, by definition. Aridity is the background physical climatology of a site based on its incoming, long-term average incoming precip and long-term average temperature, and the water balance that arises from that.
So to piggyback on Leslie's question,
You're going to keep trying to make me answer this, aren't you?
well, this is the question.
Okay.
Increased temperature, increased development, increased population. Where's our water going to come from?
Yeah. It comes to the, that's,
I can
that's
answer
right.
that. Apparently magic is the answer. Yeah, that's right. Another question right here.
Well, this is more of a comment, I guess, than necessarily a question, but it seems like the increased evapotranspiration ought to be taken into effect when developers plan what kind of vegetation they're going to put into a community and around houses and things like that. Because if that's the case, then drought-resistant plants are the rule.
Yeah, I agree. I think everything I know about Arizona climate, even if we didn't have the aspect of climate change, it seems like prudence with water makes sense. Like we don't need to have a climate change discussion to have good discussions about water, right? But it's now being sort of used as a lever, which is fine. But to your point, right? Maybe that would make sense anyways.
By the way, climate change, increasing temperatures, drought are not even factored into statewide or regional water planning.
Okay, my question is, I have heard that some people want to cut down all the juniper trees because they're soaking up the water. Is there any evidence of that?
That's out of my wheelhouse. Yeah, there's a lot of interesting discussions going on about water use of plants and using different mitigation. Jeff, do you want to take it?
I'll just say that a lot of the juniper management that's going on is based on wildlife management rather than water management. The
water management side might be more smoke and mirrors, because you can look at the Beaver Creek watershed study and other historic paired watershed studies and learn that they might be plucking the wrong data or plucking data selectively when they're trying to increase water by reducing geofluid.
That is exactly right, and there's abundant evidence to prove that.
Thank you,
So-
Jeff. Thank you. They'll go to Jeff now.
I just would like to mention there was an article I read in the Sierra magazine. I don't know if it was a recent issue about the temperature changes in Phoenix, and that like over the last 10 years, the low nighttime temperature is 12 degrees higher than normal.
Yes.
And a lot of that could be the amount of parking lots and cement and the heat retention.
Yep.
But they talk about the temperatures increasing there and the amount of deaths. But it's pretty if you want to pick up the Sierra Club magazine or join the Sierra Club, it's an amazing article.
That's urban heat island, and that is a real thing. That's absolutely a lot of the trend in Phoenix, for sure.
So what you've said about drought is it ranges from about 20 years to about 40 years. Is that typically right, or?
Yeah.
I mean,
So again, this work comes from the tree ring reconstructions to get us a real long, deep sample. And they averaged, 20 to 40 years with some outside events that were 60, 70 years. Yeah. There are some long, deep droughts, much, much longer than the current drought in the tree ring records. Yeah.
Thank you.
Yes.
I was a natural resource manager. I heard you speak before, by the way.
Good.
How about this, going back to that question again, there's been some talking points like the last 200 years have been the wettest period over the last 1,500 years, tying that into the dendro studies and stuff, or do you have anything that would or even support that or confirm it or change the numbers?
Yeah, I think I may have thrown in a lot of back pocket slides that I did not make you guys suffer through, which is, this is a reconstruction from the Laboratory and Tree Ring Research for the Yavapai County Climate Division, and it's 1080 through 1988. And so this is what it looks like. So I don't know, can you make that assessment? I mean, you could certainly look, this is a fairly wet, but we also have some pretty deep droughts in here, right? So you look at I'm sorry, so this is wintertime, November through April precipitation percent of average. So 100 is the average for each one of these years. And then we can go from 1080 to ending in 1988. And so you can see this is the wet period of the 80s, the pluvial here. So I think they kind of wash out. They kind of wash out, right? You get a dry and a wet. I mean, the variability is higher here, right? And then we can look in the historical record and see some of these longer droughts, which are really low precip for many years, winter precip for years strung together, right? Background climate variability of Arizona right here. Great question, thank you. Ed.
So our current presumed low precipitation that we're seeing in recharge records and we're seeing in stream flow records is still well down within the drought category.
Yeah.
And so it's not appropriate to say that this really is aridification.
See, this is the thing.
That's the one. Yeah.
Yeah, it's going to be a mixed signal, right? So at this point, and this is kind of back to the attribution question, would be the studies in the West show the recent drought and overall drought conditions primarily due to natural variability with an added enhancement of temperature, right? So in the future, though, as you get to temperatures way outside, I mean, this is, 10 degrees is not 1 degree. We're dealing with 1 to a couple degrees of change over the last couple of decades. further out, as that continues to go up, you do then start to see, the contribution of precipitation variability and background evapotranspiration the temp muscles its way in and becomes a more dominant effect. Those are some of the papers you sent me where you see like the drought conditions at the end of the century show permadrought. And that's largely because of the temperature component. It does not reflect the precip component. The precip component, again, is in the models is natural variability, decadal variability, some slight drying in the winter, the springtime, that track receding a little bit, but overall, that variability increases under warming conditions. So, yeah.
Okay, let's have one last question. Who wants it? Okay, we're all questioned out. Kathy.
Hi, Dr. Crimmins. My name's Kathy, and I am a fellow U of A Wildcat.
All right.
Go U of A. My question is about the asphalt concrete jungle that Phoenix and Tucson, with the rampant growth, has produced a huge amount of heat, and how that affects our monsoons.
Yeah, okay. That's a good question, and it actually has been studied. There have been some suggestions that there's been a large contribution to change in the monsoon with the urbanization. The studies that have come out recently, both observational and modeling, show a real small effect right in Phoenix, but not large scale. So there isn't any reorganization of the monsoon from the urbanization that can be detected. So.
Okay, great. So this is maybe unexpectedly complicated, but I think to me, just to summarize this, what I see is that Dr. Crimmins has made a really clear distinction between variability in the short term and long-term trends, weather versus climate. And I know that this is a very difficult concept for most people when they think about climate change. So that's real clear. So thank you very much.
Thanks for having me. I appreciate it.